Hey Kevin, how you going? Just want to talk you through the results for our design practical that we did today. I've got the data inputted into my spreadsheet, so I just want to go through what I guess these numbers mean. We had two groups doing the practical today, and your write-up is going to be strictly based on the variable that you investigated. So this top section of the spreadsheet here is for the group that looked at the voltage versus the mass of copper electroplated. So you guys will solely be looking at the top half of this data here. And the second group is looking at concentration of electrolyte versus the mass of copper electroplated. So you guys will just be looking at this bottom set of data here. So first of all, I'll talk about what the columns are referring to so you have a bit of an idea what all these numbers mean. And then I'll kind of break into the specifics of each group a little bit so you can look at the part that's relevant to you. So first of all, we've got the voltage written down here. So this is our independent variable. The bottom group has the concentration of their electrolyte solution. The rest of these are the same. So basically we've got the initial mass of the cathode and the final mass of the cathode, the initial mass of the anode, the final mass of the anode. And then we've got the initial and final current, which is basically looking at the current that's going through the solution during the electroplating. And what we want to do is get an average of this current in order to minimize the error that's accrued throughout the experiment. Because essentially, current is based on the amount of electrons flowing through the electrolyte solution, and that current will change depending on the amount of electrical resistance. And there's a number of factors that come into play with electrical resistance. It's the concentration of ions in solution. There's other aspects as well. Basically, we just want to try and minimize error a little bit, so we'll get an average current here. And then we've got change in anode and cathode mass, which is what these graphs are based off of. Now, all of this stuff here is to calculate the theoretical concentration, the theoretical mass of copper electroplated. And that's based on the information that I put on your task sheet. So that's this information here. So it's got to do with Faraday's first two laws of electrolysis. So basically the calcs are here. So we can calculate charge, moles of electrons, or Faraday's, the moles of copper, and therefore the mass of theoretical copper electroplated. And there's an example calculation here. So I encourage you to look at that, just to have a bit of an idea of the variables that come into play when we are doing this experiment. So essentially the molar mass of the substance matters. So the fact that we're using copper as opposed to any other metal, that actually makes a difference. The current makes a difference. The time being electroplated makes a difference, etc., etc. So the calcs are here. So basically to calculate charge, we've got the current multiplied by 300 seconds because we plated for 5 minutes. We've got the number of electrons, which is to do with molar mass, number of moles of electrons, number of moles of copper, and therefore the mass of copper. So basically, it just all spits out an answer here. So if I look at the specifics for the first group, so the first group is the voltage versus mass group. Now, this group, we weren't able to get the two trials completed. So we got trial 1 completed in full, and trial 2 we had a couple of tests done, and the rest we didn't get up to. So we've got a graph based on that. Now what this graph is showing us, the grey line is the theoretical mass of copper that should be electroplated for these voltages. So we can see that grey line there. Now what I've done with the anode, I've swapped it so the change in anode mass is positive, but that indicates a loss, okay? Because an anode loses mass during electroplating. So even though these numbers are positive, it's indicating a loss. So we can see here the anode loss is pretty much bang on with the theoretical, apart from maybe this here a little bit. So that tells us that there's very little systematic error in terms of the anode losing mass for electroplating. It's pretty much exactly as we expected, which is a good thing. It means we've set up that practical pretty well. The cathode, in terms of the mass being plated on is quite different. So we can see that 0.5, spot on. 1.5, spot on. 2, spot on. 3, spot on. But we've got error here and here. And maybe here? I'm not sure how that's working. I don't know where that data point is. You might have to look a little bit closer at the actual numbers. But it varies quite wildly here. And for these two, specifically this one, we've got a larger mass than we expected being plated on. So what does that tell us? Is that random or systematic error? Okay. Now, because this is a graph of one trial, it's hard for us to tell whether it's random or systematic error. Okay. It's likely to be random error. And what error might you expect? The fact that there's more mass being electroplated than expected. So have a think about the process that we did when we removed that cathode and we rinsed it and dried it and then weighed it. How might that error have come about? So that's something that you need to talk about. Okay. So the second group, you guys got 2 trials done. I had a 0.8 mole per liter concentration, but we didn't get results for that. I'm not sure if that was something to do with the fact that that solution maybe wasn't made up, or maybe that wasn't in the results table I gave you. I'm not sure why we didn't do that, but that's okay. I made you graphs too, and you're welcome to steal these graphs and change them to look however you want. You're welcome to take these numbers as well. You're expected to format this in your own results table, because obviously you're not going to just present these random numbers everywhere. You're going to format a table in your report to make it look nice and neat. Now, I've highlighted these numbers here because for the concentration, we measured the current once, and we used that number for the calcs here. The reason why I've highlighted this is because we didn't actually have, I didn't have a current measurement from you guys for trial 1. I don't know if you forgot to record it. I'm not sure what happened there. You've got it for trial 2. So I've literally just put the same thing there. Now, that is not what actually happened in the prac. So that is essentially a mistake. So that's something that you need to write about. And the fact that I've just substituted those numbers, the same numbers, okay? Because that's a source of error. So you guys, the graph that you've produced is interesting too. So all of these results are pretty much bang on the theoretical, which is good. Then the last result is massively incorrect, okay? So the anode mass is actually greater. So the anode gained mass, and then the cathode lost the same resulting amount of mass. No, sorry, the cathode gained mass too. Hold on, let me look at this properly. The change in anode mass is negative, which means the anode gained mass, and then that gained mass too. So basically, I know that's kind of weird because they're opposite, but they did the same thing. Because like I explained earlier, I've changed this around so for the anode, it's a positive number means it's lost mass. Okay? So they've both gained mass, which is impossible. Okay? So there needs to be a source of error there. This theoretically cannot gain mass. This should gain mass, but it's gained far more than we expected. So there's really 2 sources of error here. Okay? Because it can't be the same source of error because they both increased in mass, but this increased in mass when it should have decreased in mass, and this increased in mass but increased in mass way more than we expected. Okay? So it doesn't make sense that it's just one source of error. So part of your investigation is to propose with evidence the types of error that we may have expected. If we look at trial 2, it seems to be far better, far closer to what we expected, which is, I guess, a good thing. You can see some slight sources of error there as well, some slight sources of systematic error where it doesn't match the theoretical. And also, yeah, so you can kind of see the extra gain in mass is correlating to the extra loss in mass, if that makes sense. So we're expecting all of these lines to pretty much match up, kind of like here. Okay. So that gives us a bit of information to work with. So remember, not only do you have to talk about your data and what it shows and the correlation and the trends, you might want to combine these two graphs to get an average from your trial 1 and trial 2. This group up here, I didn't mention this previously, but the only thing you can do with these two numbers is to talk about or compare this number to this number to talk about random error, and this number to this number to talk about random error, because theoretically they should be the same. But from what I can see here, just a quick look, they're actually far different. So that shows that we have a random error in this experiment. So not only are we talking about random or systematic error and interpreting your data and I guess figuring out the trend and all that kind of thing, you're also evaluating the practical method. So you're saying what was good about the practical method, and then maybe what were the downsides of the method, and maybe perhaps where that can be improved. So you're evaluating your skill set throughout the practical and maybe the positives and negatives about it. So hopefully that helped a little bit in terms of interpreting your data, and good luck with your report.